Hi, everyone. I'm Jeffrey Zhang, and I'm going to present to you a presentation on 5G networking. This presentation covers content that this paper titled 5G, a tutorial overview of standards, trials, challenges, and deployment and practice. I'll be talking about the things that were discussed in this paper, as well as information from a few external resources. And this paper was published in 2017 by Shafty et al. So the basic problem around why we need 5G is that there's a huge amount of data being communicated over the network. This paper cites a number which was 291.8 exabytes by 2019, but obviously since this paper was published in 2017, they don't have updated numbers, especially with the numbers that have come out recently due to much higher online use of video conferencing and related technologies due to a lot of work being remote. So a more updated metric is that in 2020, the World Development Report estimates that there's around 3 zettabytes of information communicated through the internet last year. And this is a whole order of magnitude greater than the number predicted in 2019. And if we were to continue on this trend of around an order of magnitude every year, that would scale out of control beyond the networks we currently have today. And the current today networks would not be able to keep up. So that begs the question, how do we scale up networks to keep up demand? And what exactly will this look like? And these problems are problems that 5G hopes to solve. So the motivation of this presentation and really this paper in 5G is to evaluate current 5G deployments on their success and failures and identify present and future challenges. So technical challenges include at a high level for 5G, improving RF technologies for 5G, such as increasing bandwidths, advancements in MIMO, and that's just multi-input, multi-output, and deployment of MIMO antenna arrays, and also network diversification. Challenges also include investigation and improvement of propagation channel characteristics. So there's a lot of issues that propagation channels might experience just out in the environments or in a user's home. And there's also different signal processing techniques that if these new processing techniques come out, it could help make 5G more viable. And then additionally, testing and deployment of networks and 5G cloud and cloud RAN architectures. So just a brief overview of 5G. 5G can be separated into 3 main categories or technologies. There's eMBB, which is enhanced mobile broadband. And this is very similar to the mobile networks we have today. But these mobile networks have, or like the future 5G mobile networks that we want would have improved performance and an increasingly seamless user experience. And what this would entail is just faster networks as well as more widespread coverage of the 5G network or just network in general. And then there's the second category, which is URLLC, which is ultra reliable, low latency communications. And here we have very stringent requirements on reliability and latency. So there's some applications that need this, and this could provide latencies of around in the order of single millisecond latencies for small amounts of data. And this, again, is if you want to have low level, high reliable connections. And then there's also MMTC, which is largely unexplored, and that stands for Massive Machine Type Communications. And what this could look like is a family of applications where there is a ton of devices on the network, but all these devices are low power and communicate only a little data. But these devices would need to be powered for a long time by probably an external battery. So this table shows the requirements for 5G, and a lot of what we have today are orders magnitudes of away from what we want for 5G. So again, there's these three categories: EMBB, URLLC, and MMTC. And as you can see, there's these KPIs, which stands for key performance indicators. And the key use case that could be applied for this key to solve this key performance indicator. And the values you see on the right-hand side are kind of the minimums that we would want for this specific KPI. So if you look, there's a ton of use cases for the mobile broadbands type of communication that 5G would offer. And there's a ton of different like bandwidth and latency requirements, as well as different requirements for different types of settings. And then there's also URLLC, which again provides this really low latency type of connection. And then we have MMTC, which that involves connection density. And there's only one kind of use case for this so far, just because it's a relatively unexplored area. And this basically just says that the aim of this technology is to support 1 million devices per square kilometer. And to give a reference, today's networks currently support around 100,000 devices per kilometer squared. So this technology would want to support a whole magnitude greater than what is currently offered today. So a couple venues or pathways that would possibly make 5G more widespread or usable are listed below. And these technological improvements have all sorts of people working on them. The first one is obviously increased bandwidth. So supporting more data as well as more devices on these networks, and then massive multiple input, multiple output antenna arrays at the base station. So you want to have base stations that can easily support many devices on the same base station, and that involves having antenna arrays that can have a specific connection to each of these devices instead of switching between devices with only a few antenna arrays. And then obviously advances in this MIMO technology would help 5G, and then as well as network diversification, because as we saw these three categories of 5G, there's a lot of different use cases, and that would require a lot of different kind of networks, and then also different waveforms to help communicate with these different use cases of 5G. So the first thing that this paper goes over is the propagation channels, because virtually all 5G technologies are bottlenecked by propagation channels, and these communicate via massive MIMO channels or channels for distributed systems, as well as millimeter wave channels, which is more of an up-and-coming technology. But for massive MIMO channels, there's difficulty in scaling MIMO channels up to massive sizes that are desired for 5G. Again, there's a requirement for 1 million devices per square kilometer. So this includes spatial non-similarities elevation characteristics, as well as model simplifications. For distributed systems, a bigger challenge is modeling the links from a single user equipment to multiple base stations. So how can multiple base stations communicate with, say, your phone? And then as well as millimeter wave channels, which is very different from existing technologies, since this offers very high bandwidth connections, but is very lossy and cannot propagate through just regular free space easily without having some sort of loss. And next kind of technology or complications is with new waveforms and channel access. So there's a large variety of 5G use cases that fall under those three mentioned categories. And these three categories will require a very high degree of flexibility, and that rules any kind of one size fits all solution, which is why we want to have new waveforms to support all these different use cases. So waveforms for 5G air interference, as well as different types of channel access. So multi-user access schemes. And one example of that is just waking up a device to send data powered by batteries. And this table on the right-hand side shows a summary of possible waveforms that were proposed for 5G air interface. And this lists the pros and cons. So another section is the trials and testbeds and deployments. So obviously, to get this 5G technology going, you have to have trials, testbeds, and deployments. And even though 5G standardization is still in its early age, there have been many prototypes and testbeds that have been built over the past couple of years. So testbeds for massive MIMO below 5 gigahertz have been developed and successfully demonstrated. And these testbeds have shown that it's possible to achieve gains predicted in theoretical studies of real-time and real-life scenarios. And then additionally, a lot of these major companies, like a lot of these major telecom companies such as Huawei, Ericsson, Nokia, Samsung, ZTE, Datang, Telecom, Qualcomm, and Intel have reported and showcased test trials with many new antenna systems for 5G. And obviously, these are a lot of the companies that have focused a lot on 5G technology. And additionally, back in 2016, there was a group in China that announced a 3-phase 5G network trial plan. And that spanned for 2 years, with the first test phase in September 2015 to September 2016. And although these 3 examples are the only ones I talk about in this on these slides, there are tons of other trials and test beds, and as well as deployments that have been adopted into either universities or studies by groups or companies. And there have been a ton as well that have come out in recent years. So another section is this 5G cloud network and cloud RAN architecture. So a couple key points in this area are that you want to have software-defined networking, as well as network function virtualization. And this diagram on the right-hand side shows just an example of this network function virtualization. And obviously, you can read more about this in the cited resources in this main paper. And this bottom diagram talks about network slicing. And this basically goes over how do we slice these networks so that different devices can utilize different layers of the network. And then there's also cloud RAN architectures that are significant for the adoption of 5G technology. So coming to a conclusion, we kind of talked about the possible approaches that we can take with 5G, as well as technologies already on their way to maturity, with practical experiments being performed. And there are still a bunch of questions that we would need to answer to kind of make a lot of these new 5G technologies widely adoptable. And that includes questions about millimeter wave technology, network diversification, antenna arrangement, beamforming, as well as how to have good channel models, because that's really significant for a lot of communication. And yeah, that's it. Thank you for listening to my presentation.